Спросите. Теперь слышно? Да не больше. Можете сказать что-нибудь?
Раз, два, три, раз, два, три.
Алло?
Нет.
Слышно. Да, теперь слышно. Все, теперь слышно. Sorry.
Где он может сказать в зуме или вот через колонки, где вы будете слышать? Пожалуйста.
Саша, скажи что-нибудь сам. Микрофон, нам будет слышно.
Да, вы меня слышите?
Да.
Отлично.
Когда Ясуши говорит, это что-то уводит?
По идее, да. Могу прибавить. В общем, если там похоже, что прибавить громкость, чувствуется.
Okay, so today our next speaker is Yasushe Икэda from Moscow State University. And he's going to talk about the quasi-durations of the universal development algebras. First of all, universal development algebra of GLN, and the question of commutativity of these quasi-durations of central elements. So I think most of you know this subject, but there will be some new results, some new computations, which Yasushe will tell us about. I hope it will be interesting. I'm sure it will be interesting, but I hope most of you will appreciate it. Okay. Thank you. So first, I want to fix notation. So we mainly work on universal development algebra. Of size D, and I wrote a matrixing element. So upper x is no. If we write matrix conclusion, then this matrix means entries are these elements. And second, I like to define generating matrix. This matrix is denoted by E and belongs to this matrix algebra. And whose matrix element is matrix unit. So this is GI matrix unit. So please pay attention that ij element of E is GI matrix, so it's a bit confusing. So but I will use this notation. I think you should just I think it may be said as follows. On the left, the subscript, sorry, the superscript is the number of the row, and the subscript is the number of the column. And on the right, it is, so to say, vice versa. Is the number of,
It's confusing.
yeah, it's confusing, right?
Confusing to
Because if you look at this, it's just a little bit inverse. So you can actually write down the matrix A as the sum of elements times these generators Eij, just the usual sum, as we usually write it. I think that's what should be said.
Next, I would like to introduce quasi-differential operators. So I'm going to explain it. Quasi-differential operators are linear mappings. Linear mappings of universal independent algebra. Satisfying these three conditions. So index ij is from 1 to d, so we have d square such operators. The first condition is it gives second condition is if this operator acts on these elements, matrix units, then we have connector delta. And the third one is we call it modified Leibniz rule. And this condition is if acts on some product f times g, then we have this kind of rules. First, it acts on f on the f. This operator acts on g. We have one more term, and this is we have another.
Excuse me. Could you comment the point 2 of your axioms? Maybe you should put the A.
Yeah, the
Okay,
difference is that this E is
Because E is a numerical matrix, it's not an element of universal enveloping object.
I see.
There should be a generator A.
You need some.
Or the universal
I think
enveloping
you should
Define just we should use define.
Yes, I think it's better to put a capital E.
Here,
Yeah.
right?
because it is just
Yes, it is just the basis of the Lie algebra,
right.
or matrix Lie algebra.
So here I should
Yeah.
capital.
A capital.
Yeah.
And here, what should I write?
Just this.
This is okay.
No, this is okay, right.
Sorry, so EIJ is a matrix,
Matrix units, yes.
But you can
So
actually
Matrix units.
but every EIJ is a matrix. It's one.
you have to distinguish between numerical matrices and same numerical matrices which play the role of elements in the algebra.
In GLN.
Yeah, in GLN.
So you just take some
So these capital E,
matrix form of GLN.
so first of all, capital EIJ is just a matrix unit, is numerical matrix with just one unit and all other elements equal to 0. But then you can regard it as an element in GLN, in the algebra GLN, and the same way you regard it as an element in the universal enveloping algebra of GLN, of GLD, sorry. And in this case, it is, I think it is natural, it is normal, I think it is, it's convenient to use separate notation for the same matrix or have it as an element in the algebra.
I would even say it is obligatory
Okay.
to use different notation because E small, it is not a matrix.
Yeah, it has
It's only a
different,
generator.
it has different properties.
So what's E small?
It's
It's a generator of infinite dimensional associative algebra.
it's a generator of universal enveloping of GLD.
Okay.
So the same matrix, but regarded as a generator. But it has different properties. For instance, here, when you take the product of matrices, you obtain a matrix again. But here, if you take products of two generators, you do not get a matrix as a generator. Just get some quadratic term.
E capital it should be considered as some representation of E
Yeah.
small.
Yes, so this just representation.
But this definition is not completed yet.
Yes, it is.
I don't understand what is generating matrix. Generating matrix of what?
Забудь. Это базисный элемент алгебры.
Тогда не generate.
And these operators satisfying these three conditions are unique and well defined. And next, I like to define an shift operator. Suppose it's numerical matrices. We define operators C summation linear combinations of these class-defined operators. So we have conjecture, which is not yet good. Such that so any power of this operator DXC to two central elements. Capital Z center. So for any two central elements of universal algebras, any powers for these operators, then these two elements commute. So this is our conjecture, which is not really. Next, I want to explain. So, until now, what is known? First, I remarked that the center of universal enveloping algebra is formulated these elements. And what we know now is so since we consider only central elements and want to know the commutation relation, and center is generated by the elements, so it is important to obtain this element. And this is we know this it concretely, and this is the problem.
It's better to write it in
Yeah.
random. And here
I explained this, what is x star plus and f star.
Maybe there is some misprint in the first term because there's no dependence on J.
Here,
Yes. The first sum does not depend on J. It is
okay.
Yes.
and the number A is twice.
Yeah.
Is written twice.
Yeah.
But the sum of them should be J.
Here. Here, f plus and f minus polynomials I'm given by here f plus and f minus are polynomials. So f plus n is here plus, and this is integral coefficient polynomial. And f minus also polynomials, but here we have minus.
So I think it is worth saying, I don't think it's either been erased, I don't know if it will be that E is the matrix of generators. It's the matrix whose entries are the generators of the Lie algebra GLM. Right?
But if we put here instead of X,
Yes.
E, so it's necessary to replace one by identity.
Yes, yes.
Матричное значение.
So the formula is really remarkable in my opinion. It looks like something you should expect from some implication of, I don't know, Yangians or something like that. Never, I tried, no, I'm not that good specialist in Yangians, but I tried to relate this to Yangians when I failed.
So with this result, it's new.
Sorry?
With the start.
This result is
Old.
yeah,
It's already published.
Yes, already published. Yeah.
Using this concrete formula, we have this conjecture for when m and n equal 1. So using this formula, we have the following settlement. Up to now, we know this already. So the topic of my talk today is so I like to extend this result for larger m and n, and I try some competition. So I like to discuss structure with you.
Now we're going to talk about some new results, and these results are results of computation. So it's really important to look at the background. It's difficult to follow all the computations.
Yeah, yeah. Computation is very hard, so it is hard. It is also hard to write on Blackboard, but I'm going to try. maybe I should. Yes, here also. So I tried to obtain the formula for second order derivative, and it is in fact possible. So I like to introduce this formula to you. It is hard to calculate, but still possible. So I have to write it down here. But only for generator. Only for generator. So general central elements are not only generators but also products of generators and their linear combinations. But for generators, we can obtain second order cross derivative completely. This is my I'm sorry that it is a bit less, but something like this.
Very calm. Define T.
So now still I don't explain. So I don't give completely, for example, what is this element, what is this element. This element means, so this is a matrix whose ij entry is dij trace like this.
So it's just psi times dij. Isn't it just the psi applied to the trace? Because when you say psi times d, it's just d psi.
Here,
Yeah.
Here.
I mean,
No, d psi means the trace of this.
Yes.
But we need to add further elements.
It's the matrix.
Yes.
Side is numerical matrix.
Capital itself is a
Numerical matrix. In the middle, it's just, okay, so we have matrix multiplied by psi. We have also matrix because fj of E is a matrix. And then you multiply this matrix by element in universal development algebra, trace of this product, right? So they obtain again a matrix with coefficients in universal development matrix. And then you apply to this matrix psi times D. So D, partial D, is the matrix where each entry is just the partial Dij defined before that. So, and it's again a matrix product. It's a kind of matrix product. And after this, you take a trace. That's really cumbersome. Any ideas how this can be proved? Is there any explanation except for sheer computations? Anything just the straightforward computations with induction, right?
Yes, in principle, yes.
Because it looks really intimidating. That's it.
But finally, it is not so easy to understand with the theorem. I guess that this theorem is intermediate. It is not finally, it's just to what? To show what? To show conjecture.
And for at least n equal to 2.
Conjecture in what situation?
For n and m equal to 2 and f and g equal to these traces.
Берешь любые центральные элементы, дифференцируешь сколько угодно раз, получаешь коммутативный. Нет, он научился 2 раза дифференцировать.
То есть он доказал эту теорему для m.
Нет, не доказал, то, что надо для любого произведения доказать.
m и n равны 2, что ли? Почему здесь 2 раза?
F любой элемент центра, а здесь конкретный. Уже посмотри, что получилось.
Да, ужас получился.
Это
Удивительно, что это можно.
Хорошо, а зачем эта теорема нужна? Она как бы, что он хочет сказать?
Гипотеза.
Подожди, это же доказано результат прямого вычисления.
Это результат прямого вычисления. С помощью этого прямого вычисления нужно пытаться прокомментировать вторые производные, по крайней мере, этих образующих элементов. Они удивительно.
То есть он хочет сказать, что даже в этом случае, при вторых производных, все очень тяжело. То есть поэтому и приведена эта теорема. Она как бы не нужна.
Вот не нужна. Она не окончательный результат.
Она ему нужна.
Да.
А мне нужен результат. Это не результат.
Она не окончательный.
Это лево.
Хорошо.
Технически.
Технически.
So we still don't have final result. But anyway, I obtained complete formula for second derivatives, and I tried to show this condition for second order.
For f and g equal to these traces, right?
Yes, more precisely, when m equal 1 and f is any central element, and n equal 2 and g is this trace element.
Okay.
So quite partial. And still, I don't explain. So here we still don't calculate this. What is this? What is this? And it is also possible to obtain this concretely. So I like to believe that so we have fully concrete formula for a second derivative. So up to second order, we can obtain a complete formula. And this element. So here this is polynomial E, and here polynomial E. So this second derivative is linear combination of this kind of element, in fact. So this element is in fact linear combination of these two types of
So the
elements.
first and the second lines.
Yes, this kind of elements and also this kind of elements. We need two kinds of elements. And this is linear combination of these kinds of elements. So now, so we know the coefficients. So we should know coefficient because this is linear combination, and we now know the coefficients of this linear combination.
So what you claim is that big square of psi is a certain linear combinations of two types of elements.
Yes. Yes.
B squares of psi of trace m. Is it only for trace e to the power m, or is it true for any central element that you get some
I thought about it. I forgot, but as far as I remember, it is also true for central element.
So for any central element, the right hand side of b square of psi is linear combination of these two types.
I think so.
Okay. With what coefficients, it is really hard to say in general case. And this combination, and these coefficients are really important, I think.
This element is a summation of this kind of element. And this is a central element.
I'm central.
So in fact, this part is essential, and we need to think about this term when for example m equals 0. So So probably
the rays something on the left or on the right. I mean the left side of the board.
Yeah. So maybe it's better to. So from now, I'm going to write this expression as a sub n minus m. And here, the sub n minus n. So it depends on the. So that I calculated computation distribution up to n square of 3. So anyway, this expression computation relations. So
You think it is not necessary
What is
to-
the restriction on M?
I think
M
it
is
is not-
less or equal to what?
7.
Sorry, I think in this situation, in this corollary, it is not necessary to put this. Yeah, if you formulate this result for any n, yeah. Okay. Yeah, because of course, if you compute for the first part and then the second part, then yeah.
Yeah.
And it's true for any. Seeing it's just I think it's just a formulation. It's actually not. I don't think it's really.
Вот эти куски этой формулы, немножко вот эти. Вот это А, и второе это Б.
Yeah, I mean, yes, if for any n, you have this. Then for any n, you have the top. But yeah, it looks just a corollary of the formula. It's a
There's
bit,
no means to check this formula.
sorry,
No means to check this formula.
this formula 11, you mean, formula 11, you mean? It's just sheer computation.
Можно проверить. If. Я понимаю, if. Но что нас утвердительные были, надо проверить, что это так.
Нет, смотрите, Дмитрий, формула 11.
Д2 это как раз сумма, это А, это Б.
Да, причем там сумма по n разная. Сумма по разным n. То есть на самом деле в этом королларе указывается, что для того, чтобы она коммутировала, достаточно, чтобы только для одного n это коммутировало, а дальше это будет, если для каждого n это. So, sorry.
The second derivative is a sum of an plus bn for various time.
Right?
But corollary says that for each concrete m, we have such a commutation.
Yes.
So evidently that we
Yes.
have the commutation.
It doesn't say that we have this commutation. We have this commutation, and we have the commutation for the sum, and vice versa, which is not evident.
Vice versa is not there.
Definitely not evident. So, okay.
Vice versa is also evident.
Everything, because when we take the sum of ANs and BNs, and it commutes with the sum, then it is not evident that it will commute with the separate element from this sum, separate term.
But
Yes.
it's something like so. If we consider n plus 1, then just how to explain.
Yeah, I see. So this corollary, the difficulty of this corollary is to
This is just
derive-
trivial. This is just
Если
trivial.
мы из 2, например, 27 берем, вычитаем.
Yeah. So it's the condition is that it's for any n. Yeah.
For n, yeah. Тогда нет, yes.
So if you say that it's for any n, it's true for yeah. Sure. Yeah, I see.
There's A1, there's A1 plus A2, Z always A2, there's A1 plus A2, Z always A3,
And so on.
Вот это совершенно сильно. Он же не той формы, как нужно.
Нет, он А. Он А. Он как А. Первый член это А.
Это утверждение, что если у тебя вот этот трейс мутируется ко второму производному, если это опять тогда мутируется.
Я понимаю, Салат, я понимаю, но нам-то доказывает нашу гипотезу не для какого члена? Почему?
Такие члены входят в нашу гипотезу.
Да, конечно.
Там еще есть что-то, но вот это.
So we want to know if this is really commutative. So first of all, so any first cross derivative of central element is linear combination of this terms over central element. So if we know this commutation relation is in fact 0, then we can conclude that so the second class derivative of this form commute with any first order derivative class derivative of central element. We don't have any reason to think that this element commutes with an and Bn separately, but
That's precisely the most difficult part. Because you always, it's always easier to assume that separate terms can be. You really need the sum.
but I don't know why, but up to n equals 7, these elements commit separately. So yeah.
It's plausible for you should be the same for any element. The separate sensitivity should code for any element, but yeah, but it's probably too.
But why 7?
Because it's as far as
Yeah, just I could manage to calculate commutation is complete and it is very hard.
Yes,
So
yes.
I could.
Почему 7? 7 на компьютере просчитывать.
Нет.
Ну правильно?
Yeah. So it's really remarkable that you could do this by hand, as far as I can understand, right? You can do this with computer, so yeah,
Only by.
that's really remarkable. I think I think it's really worth experimenting with computer. Computer shows that these can be extended further to say something like n equal to 20, and it is almost, I'm almost sure that.
Инженер подозревает, что 60 делится на все числа.
Yeah, it's like this.
To be honest, I'm still not sure these elements can be separate for arbitrary n or only for some special phenomena for only
Small n.
small n. I'm not sure still now. But after n equals 7, these
So it's
elements
really pretty large. So.
commute separately. The n and bn commute with these elements separately. So next, I want to explain. So what helped me to calculate this balance? I got some technique. So I believe that it is enough to calculate this down. So I have to explain it. So in my opinion, the following observation is crucial for computation. We only need to know two formulas. Suppose that zeta equal finite sequence. So this means that so each entry zeta k is either numerical matrix or generative matrix. So we consider this kind of sequence. Then we have the following. The first one is this kind of commutation relation. And this is given by this formula.
Okay, so we just the place where psi k, zeta k is equal to e, we put this commutator.
Yes, exactly. So this is just a product. Product to calculate this commutation relation. Yeah, we need to find we need to find the place where the generative matrix is put, and we need to replace this generative matrix by this commutation relation and take summation. Then we obtain this graph.
And in this sequence, we should have only one E.
No, any arbitrary number.
Yeah,
Another number of
Yeah.
E, but
In arbitrary places.
another place. But what does it mean? The sum S
Yeah.
It's all places where zeta
Yes,
k is
yes.
equal to e.
We only need to
All the other
sum only.
означает, что вот у тебя последовательность некоторые матрицы из универсальной вертикали. Когда у тебя будет сумма, каждая такая матрица заменяется таким коммутатором, все остальные стоят такой версии. В каждом месте, где она возникла, такой коммутатор.
Second commutation relation which we should know is the following. So this is matrix, this is also matrix. So this is commutation relation of these two matrices. Trace of this commutation relation is given by this formula. Minus we have a concrete way to prove this computation.
Trace of this data of this matrix is equal to the sum of these traces.
Yes, some of these traces.
And again, we split the sequence at every place where psi zeta k is equal to E.
Yes. Of course. So for our purpose now, this is enough. But as you can easily see, if we want to calculate more higher order of derivatives, then it is definitely not enough. Because here, so
This is the first one.
yeah, so this means we only need to calculate the first order derivative. So for our purpose, these two formulas are enough. But if we want to, for example, n equals 3, n equals 4, and so on, then we need much more complicated formula to calculate computation relations.
This EM, as far as I can understand, just one because you probably know more than I do about Yangians. This EM is the matrix of generators of Yangians, right? If you just consider it, if you just take the products of if you take a generating series of and multiply it by this formal variable inverse U, and we get the generated matrix of Yangians. Just wonder whether these formulas can be somehow boiled down to something known for Yangians. No, these formulas should be known to specialists in Yangians. Just commutate, you just commute certain generators. Right? It should be some. Oh, it looks pretty much like the this beta. No idea how this can be. Enough. They didn't know Yangians well enough to prove this with this group. Didn't hear what I say. I mean that you can actually now take the generation series.
Which one?
I mean, EM, we have EM e to the power n, right? Yeah. You can take the sum over all m's and multiply it by some formal variable, and then you get some formal power series matrix, Tm, right? T of u. And then this looks like a commutator if you just take the sum of these relations. They will look pretty much the same. So you get some relation with this whole power generating matrix. And this looks like some relations in Yangians. Yangians are certain algebras which are obtained if you, so to say, look abstractly on the elements of e to the power m as new generators and use the relations which are this but you don't know. In Yangians, you can actually find some large commutative subalgebras. They are called beta subalgebras.
So how did you get this? So how did you prove the commutativity in Yangian?
Yangian, they have a very nice commutation relation, very written down in terms of matrix, which Kyle showed us last year. So here we don't have our matrix actually, but this is hidden somewhere. But now it looks like something very close to Yangian.
Shortly speaking, I use these two formulas to calculate. So using this formula repeatedly, then I got this result, shortly speaking. But I don't know how to generalize it. So this is only for small n. So I wonder how we can generalize this result to arbitrary n and more general, so higher order and so on.
But the term AN looks much more, say, friendly than BN. So maybe you can prove at least the first commutativity for large N's.
You mean completely?
Yes, if
It's still hard.
still hard, even for A.
Yeah, I think I
Там
also
еще
did
производный
one
стоит. Он записан компактно, а если ты раскроешь это производное, то у него опять все вспомнит. But it seems to me rather strange the following, that 7 is already a large number.
Yeah.
If you have succeeded in computing all this for n is equal to 7, why it is not, I think it is not much difficult to compute this for anything. What is the advantages of small m?
I didn't.
For example, if you compute for n is equal to 1, 2, I understand, but if you have succeeded in computing for n is equal to 7,
Yeah, that's what I think. So, yeah,
it's
really-
already enough in order to compute for n.
Can you
Just change 7 for example, n grade.
But when you do the details, maybe there are some properties which really stuck out.
Понимаешь, если у тебя вот это а, она как-то вот все время меняется, а потом, когда n больше 7, она наконец перестала вот принципиально меняться, тогда я бы еще понял. Ну как вот, это топология. В размерности 3 некоторые особенности, которых мы больше не видим. Но я думаю, что какие-то peculiarities могут быть для n равно 1, 2.
Может быть, 4.
Да, но уже дальше.
Ясуши, did you use any computer calculations for that?
Did you use any computer calculations? Did you use any computer calculations?
No, only by.
Ну что, для 8 времени, что ли?
Нет, я просто нужно, чтобы
Запрограммировать.
I think you're now learning this mathematics, both from mathematics, and maybe even this will work out. But, you know, it's really very remarkable that you can do this by n till n equal to 7, but then.
I heard that in mathematics, the commutative algebra is not very visualized.
Yeah, I heard the same thing.
There's some other analytical packages.
Unfortunately, we don't have Ira here. He's done lots of non-commutative computations using Wolfram mathematics, so she would probably judge this. She's not present here. Okay, so I think if we have some time, we probably we can either stop here, I believe, right? As far as I can understand, it was your intention to stop here or not.
Yeah, it is also possible to show some concrete computation, but
Yes, that's precisely what I was. That's precisely what I was about to suggest. So we can either stop here, we can look at some concrete computation with not so large n. They say n equal to 3, maybe, or 4. Can you? I think the first equation with n equal to 3 would probably do.
maybe so.
Вообще, я думаю, что технический результат, так сказать, не надо показывать. Вообще, можно здесь.
Не знаю.
Но это утверждение. А предыдущие, так сказать, они как бы древние технические.
Мне это нравится, потому что они проявляют некоторую, проясняют некоторую как бы связь с индианами, но неизвестно, какую лично имеют.
Вот связь я так не понял. Значит, по твоему мнению,
Посмотрите, возьмем матрицу образующую этого индиана.
Ну, e в степени m подели на u в степени m. e в степени m это
Просуммируй.
скобочки. Просуммируй пока. Получишь матрицу L. И Гоша говорит, что z подсчету вингяна.
Ну, это просто нет. Что такое трейс e в степени n? Что такое e в степени n делить на? Это матрица, образующая индиана. Тут написано некоторое соотношение. Потому что опять раскрываем, и надо обнародовать. Вправо. А вправо мы хотим обнародовать. Меньше, чем степень n не дает.
Не, ну, если бы того, это тоже не страшно.
Тоже не страшно. Вот.
Even
Look at this computation for some small n.
Maybe I can explain some atmosphere of calculation.
Okay, sure.
So this is only part my calculation. But for example, I needed to show this kind of formula. For example, I needed to prove this, calculate this formula.
So if this formula holds for any I plus j equal to n,
3.
so all for 3, and 4 equal n equal to 4, this is not true, for instance. But I think you have certain formulas for all sums of I and j from 3 to 7.
This is not true for bigger. So if we correct here to arbitrary elements, then this is not true.
This is not true. The sum, if you just take the sum, but for, until 7 it is true.
No,
Not even for 7.
not even until 7, not true.
Okay, then you just really want to know what.
As far as you know, if here is 5, then it is already.
But still, the sum of A and B can use.
Yes, still, yeah. A and B, A and B. So using the second one, it is easy to show that part. So here we can change the order I of j. It is followed by the second of this error. So using this, then this is right. So the left hand side of this equation is like this. And then next, using the first formula to calculate this expression. Then, for example, the first computation relation, then using the first formula, then this is we put commutation relation to the first B,
And the second,
secondly second generated matrix and third matrix, and so on. Then So finally we obtain some expression, and we can also compute computation relation with this and this, and the result of this sums of computation relations is I only write result, so this one we obtain trace square C and so E exactly yes. So calculating this, then we obtain this. Then this time we can use this formula to calculate this more. Result is yeah. So using this one, then we obtain this is result is I don't write down the computation or the computation, but you can get this using the formula. And this is we can move numerical matrices to the left side or right side inside the tray. So this kind of computation is a typical computation. Just we use these formulas. Yeah.
Remarkable that
First one, second one, first one, second, and finally we can do something is there.
these kinds of computations usually call for all possible ends, but it's really remarkable that for n equal to 5, something is left, right? And
Yeah.
for n equal to 6 again, right? But it cancels out the something which comes from the second term.
Yeah, yes. So cancel with different term from some different term.
Yeah, that's really remarkable. And, that's good to go. Yes. Because actually, when I was thinking about this, I was sure that, well, if it was more or less not clear, it was more or less plausible that the second derivative would contain the terms of the second type. Sum of traces psi ei, psi ej, all I and j's, sometimes the sum is fixed, right? It is more or less evident that there will be such terms. And I felt like in order to prove that cumulativity, you just need to check that such terms always commute with the terms of the first type. Then it turns out it's not true, they do not commute. Separate terms do not commute, that's more or less clear. But the sums, they don't commute either. You need something else to cancel out the additional terms. And that's really also surprising. Okay, thank you very much. Well, I think it was interesting, very interesting. And I believe that maybe. Okay. Any questions or comments? Okay. Then let us thank the speaker. And Дмитрий,
Ну, я не хотел бы, честно говоря, просто. Ну, если ты настаиваешь, а? Нет, прям четвертый.
вы могли бы, если вам тяжело, можно, конечно, просто прийти, можно сделать это онлайн. Как вам удобно.
Онлайн это еще хуже.
Это еще хуже.
Ну, это как вам.
Нет, ну, в принципе, так сказать, Паша ведь как бы здесь, я думал, излагал уже все наши новые результаты касаемо
Когда мы
Ни Кукапелли, ни Куфрагинуса.
Ну, хорошо, ладно.
Спасибо. Тогда я...
Ну, тебе надо сам прислать, наверное, аннотацию.
Конечно. Ну, можно там прислать.
Я в четверг пришлю, потому что я завтра в Питер еду. Просто сам
Хорошо. So next time, Dmitry Ilyich will continue. He will tell us about Capelli relations and Arrhenius equations and so on. Transaction equation analysis. Okay, thanks.
Спасибо.